Hello everyone, my name is Saleh Al Khalifa. I am joined here today by Gabriel Kuchakovic and Niall Name, and the three of us are proud to present our projects for our CS5800 course concerning the application of graph algorithms for running route optimization. So before we go ahead and dive into the specifics of our project, I'd like to go ahead and give you an idea of a little bit of background information to set the stage. So to give you a sense of where we're coming from, we live in the city of Boston, and one of the most famous annual events in the city of Boston is the Boston Marathon, which was established in 1898, almost 125 years ago. Given that the Boston Marathon is one of the top marathons in the world, the ability to qualify for this marathon and be entered into it is a very rigorous and time-consuming task, requiring runners to have a great deal of practice in a number of different areas. And so while many marathon runners are from around the world, many of the participants, especially within the Boston Marathon, are from many dense cities such as Boston. And living in a dense city makes it very, very difficult to find an optimal training path, and being able to do so is a very, very challenging task. So with that in mind, the problem statement that we formulated here is that there are many different types of technologies and devices used on a day-to-day basis, but very specific to cars and being able to travel on roads and whatnot. And it allows users to find different types of optimal paths to get from one source to a destination. However, there are not that many solutions similar to that that offer similar capabilities for runners, especially those runners who live in very dense cities such as the Boston area. And so, given the many different types of algorithms that we've covered within the confines of this course, specifically graph-related algorithms, we wanted to investigate the use of several of these algorithms specifically to help address this gap for runners in the Boston area. Now that we've covered a little bit of background information relating to this project and we've taken a look at the problem statement relating to the particular question that we were trying to answer, let's go ahead and walk through some of the methods that we applied within the confines of this particular proof of concept application. So looking at the left-hand side of the screen here, what you see are the 5 different methods that we applied. And for each of these methods, we summarize the main application of which type of algorithm was used, as well as the use case associated with that algorithm. So starting off on method 1, what we see here is the application of dynamic programming for longest limited path detection. And the main use case that we wanted to solve here was the fact that long distance runners may want to find the longest path possible in a small neighborhood to maximize distance, but limit that to a particular amount given their particular preferences. Within method number 2, the idea here is the application of the shortest path via Dijkstra's algorithm. And the main use case here is that, contrary to our long distance runners, our short distance runners may want to find a direct path from one particular source to a given destination. Method number 3, on the other hand, concerns the application of interesting site prioritization. So with this particular item, think traveling salesman problem. The main use case over here is that users can visit or may want to visit certain interesting sites in Boston to enhance their running experience. Method number 4 was the application of finding particular routes with specific distances while avoiding what are known as bad roads or not so good roads. And the main use case here is that users can enhance their running experience by prioritizing very specific paths that are of higher quality given a certain distance. With that in mind, think items with a little bit more traffic or not as much running space, if you will. And then finally, method 5 concerns the application of generating a path that maximizes the number of interesting sites to visit. And the particular use case we address here is that, say, given a particular distance, users can enhance their experience by visiting very specific sites in the Boston area. So now that we've talked through some of the different methods that we applied as part of this proof of concept application, let's go ahead and talk about some of the data that we used to prepare our particular graph. So to demonstrate the feasibility of the algorithms that we just discussed, we prepared a graph representing a small neighborhood in the Boston area in close proximity to Northeastern University. What we did over here was utilize a particular library known as NetworkX to go ahead and draw and save that graph using the Python programming language. We drew the map using Google Earth and traced that distance measured in meters using NetworkX. We then converted that data sets that we obtained into a couple of different structures, the first being an adjacency list as well as an edge list. In addition to these two, we also exported that as a adjacency matrix, all within the form of a CSV file. What you see on the right-hand side of the screen is a representation of that particular small neighborhood in Boston. So with that in mind, let's go ahead and dive into the 5 particular methods, with the first being method number 1, the idea of the longest limited path. The main idea here is using an algorithm specifically within the confines of breadth first search, or BFS, and apply that to our particular algorithm, or excuse me, our particular graph to identify the longest distance possible. What you see on the left-hand side of the screen is a summary of that particular algorithm, and what you see on the right-hand side of the screen is the actual code written in the Python programming language that represents that particular algorithm. On the bottom left-hand side of the screen, what you see are 2 different maps, with the first map on the left-hand side being the original map, and the map on the right-hand side being the algorithm, or the map that the algorithm was able to determine as a path of interest. Notice that the path starts off at 0, it goes to 4, 5, 8, 18, 23, 27, 28, back to 4, 5, 3, and 0 again. Again, the idea here is that a user can input a particular space or a particular target, advance towards that target, and identify a path that is limited by the particular distance that they input in there. In this case, the distance was not limited by the actual length of each of the edges, but the number of nodes. But users can go back and forth. It's completely dependent on the user's preference. Ultimately, what you see over here is a summary of that first particular method. The longest path problem is a well-known area that involves finding that maximum length given a particular graph network. This problem is an NP-hard one, as opposed to the shortest path, which is an item that can be solved in polynomial time. Now, given the fact that we want to allow the user to limit that length of the path, we use the BFS algorithm to enable this particular functionality. Keep in mind that the time complexity of BFS is O of V plus E, in which V represents the set of nodes and E represents the set of edges. Now, given a particular use case which focuses on relatively smaller neighborhoods in the Boston area within running distance, we do not really anticipate users reaching higher values for these nodes and edges. However, in summary, what we managed to do over here was develop an algorithm in Python based on BFS with a few minor alterations that allows the user to find a long path given a particular neighborhood, which can be limited based on the user's preferenses. So with that in mind, let's go ahead and dive into method 2, Dijkstra's shortest path. The main idea behind this method, again, is conversely to the longest path that we saw a moment ago, was an item catered towards a shorter path, something for our short distance runners. What you can see on the left-hand side of the screen is the pseudocode for this particular algorithm, and on the right-hand side of the screen is the actual code itself written in the Python programming language. What users can do is provide the start and end nodes of their particular path, or their path of interest, and what the model will be able to do is produce an ideal path based on what the shortest path would be. What you see on the bottom left-hand side of the screen over here are 2 different maps, first representing the original map, and then the second one representing the determined path per the particular algorithm of interest. So it's important to note that the shortest path problem ultimately has the objective of finding a path between 2 nodes in which the sum of weights between them is minimized relative to the other ones. And there's a number of different ways to solve this. There's the Bellman-Ford algorithm, the Floyd-Warshall algorithm, as well as Dijkstra's. And for the purposes of this particular proof of concept, we only focused on Dijkstra's algorithm. And so in this previous method, in method number 1, we focused on long-distance runners again, but the idea here is doing this for short-distance runners. In this algorithm, the time complexity is as the result of the edge of, for each of the edges is O of E, and the complexity for each vertex is going to be O of E. So given our implementation, we reached a time complexity of O of E plus phi. Given that we did not use a priority queue, that could be an area of future improvement, would be to use a priority queue in order to improve our time complexity. So with that, let's go ahead and move over to method number 3, which is the traveling salesman problem. The main idea over here, again, is being able to visit certain nodes of interest within a given graph network. On the left-hand side of the screen, what you see is a very high-level summary of that particular algorithm, and on the right-hand side of the screen, what you see is the actual application of that algorithm within the confines of Python. It's important to note that this is not an algorithm that we developed within this particular proof of concept. This is actually an algorithm that we discovered while using the NetworkX library. So it's actually within the approximation class, and it is a function known as traveling salesman problem. We wanted to use this particular application because it was a great way to demonstrate the use of a greedy algorithm for the TSP problem. So again, the main idea here is that the user can enter certain nodes that they want to visit. And in this case, we entered 0, 20, 18, 9, and 27. And what the model is able to do is produce a particular path within the confines of our network that allows the user to visit those nodes in the shortest distance possible. Again, the traveling salesman problem is a very well-known and well-studied problem in the field of CS, and in this project, our objective is really to implement that greedy approach to solve this issue, just to allow runners to be able to target certain locations to increase both the quality and experience of their run. And so again, we use Network X to investigate this particular item, and we specifically focused on one implementation that they had, a greedy implementation, although they did have many others. And so given this methodology, what you see on the left-hand side of the screen is the associated time and space complexity for this particular algorithm. The next method that we'd like to introduce, method 4, involves finding the best route for a given set distance. The main idea here behind this particular algorithm, and contrary to methods 1, 2, and 3, the main idea here is optimizing that particular path or that particular route of interest based on the user's input of their desired distance that they wish to run that day. The main pseudocode that you see behind the algorithm is represented on the left-hand side of the screen, and the actual code for this algorithm you can see represented on the right. But the main idea there is by using a different set of weights for each of the different routes, what you can do is also represent the quality of that road. So in other words, think of this as a method by which users can identify the best path of interest that is very specific to the distance that they would like to run, but trying to find the highest quality roads or the best quality roads for them to run on. Quality can sometimes be represented as either less traffic, less obstructions, or an overall quality estimate depending on what the user's preferences are. What you see on this slide is a summary of method 4. Again, the main idea behind this method is that it was designed for those considering to run for a given set distance and try to avoid bad roads. The concept behind this is very similar to while driving. Many of the applications that allow drivers to find optimal paths help them avoid traffic. The same idea applies here, but instead of looking at car traffic, we're looking at people traffic instead. What this algorithm ends up giving you is a list of paths that all give you some ideal routes that fit this particular criteria. And ultimately, the time complexity, if memorization was implemented for calculating the current paths, it would be something along the lines of O of n plus m. Finally, let us now visit method number 5, the idea behind visiting interesting sites along your run. Unlike method number 3, where we implemented or tackled the traveling salesman problem, method number 5 implements a similar algorithm. However, unlike method number 3, where the objective is visiting nodes in the shortest distance possible, the idea here is visiting the most interesting sites given a predefined set distance. If I could draw your attention to the left-hand side of the screen, what you see is a summary of that algorithm within the confines of its pseudocode. What you see is the original graph, the reduced graph, as well as the reconstructed graph. And on the right-hand side of the screen, you see the code associated with that particular algorithm. Ultimately, at the end of the day, as opposed to the traveling salesman problem that we tackled in method number 3, the idea here is that you can implement a very similar algorithm. However, given a certain distance, it returns a path that visits the highest number of interesting places. So instead of the user defining which items they want to visit, what they can do is set a distance, and the algorithm will try to identify them on their behalf. Ultimately, the idea here is the application of Dijkstra's algorithm. A future enhancement that can help reduce the number of nodes can be used by filtering out a certain set of items prior to applying the algorithm. To summarize our project, within this proof of concept, we developed and implemented 5 different algorithms and methods that addressed many different runners' needs within the confines of our particular use case. We introduced 5 features represented by 5 algorithms over the course of 5 methods that helped runners find ideal routes in dense cities such as the city of Boston. The capabilities that we successfully introduced into this particular proof of concept included the following. The first was the ability of long-distance runners to find long paths given a certain distance. The second is the ability for short-distance runners to find the shortest path given a certain distance. We also included the ability to visit interesting sites based on the user's input of which sites they wanted to visit. In addition, we included ability for users to find the highest quality paths based on the sidewalks or the least amount of traffic, depending on the user's input. And then finally, we introduced a method by which users can maximize the number of interesting sites that they wanted to visit based on the given distance at hand. Thank you so much for listening, and have a great day.